everyone, all the techies and data enthusiasts there. So guys, this is video 8 of our transformer series, and in this particular video we are going to discuss about decoders in transformer. So previously we have discussed about masked multi-head attention, before that encoder. So if you have not watched those particular videos, do check out. Video links will be in this video description. In today's video we will visually understand. So I have created some important images out, very detailed explanation video where we will be discussing about decoders, what is decoders, and how crucial they are for transformers and how important they play a role. And also I'll give you an examples of decoder models which are creating revolution. In short to say, even the chat GPT which you are using now, that is also a decoder based model. You all know in transformer you have encoder decoder architecture, right? So the decoder model which you have, the decoder architecture, stacked of those decoder is only called GPT, which is nothing but generative pre-trained models. So those are the models which you are using right now in your chat GPT. So I'll explain you all in detail about that. If you have not subscribed the channel, do subscribe the channel and on the bell notification. So guys, now let's get started. Overview of decoder. The decoder in the transformer architecture, right? It generates the sequence based on mainly two inputs. One is the encoder output and the target sequence. So the encoder output is nothing but the generated embeddings from encoder architecture. The final answer which you get from the encoder architecture, those embeddings are again feed to decoder, and the sequence of tokens are generated with a special starting point called as start token. Okay, what is start token? We'll discuss about that. Before that, you need to understand output shift to the right, which is nothing but you have a word here. For example, here you can see the word, the cat sat on the mat. The expected output must be like the cat sat on the mat and end. So here, what does the target shifting one position ahead means that shifting towards right. So here what we do, we add start token at the beginning. So are you confused? Don't worry guys. So you have an image at down here to understand that in detail. So you have a start token, right? That what we do, we shift the sentence a bit aside and we add a start token at first. One position ahead and we add a start token at there to understand it properly. So here you can see the example here. The cat sat on the mat is the output sequence. Then the target sequence will be start, the cat sat on the mat, and the end also will come. So here you have a clear image. This output sequence, again, don't get confused. These are the embeddings output sequence. Encoder embedding output sequence. Input to the decoder. The target sequence is the sequence of tokens that the decoder has generated so far. So it will start with a special token called start, includes all the words expected output sequence, and end with the end token. So we add start and end token both for this particular sentence, or not only for this particular sentence. Normally whatever we feed in, it will have start and end token. Do you all have any guesses why we add this mainly? So the main reason why we add this start and end token, right? So that the particular model which we are going to feed the data or fine tune, it understands, it uses the auto-regressive manner, and it understands like clearly the sentence starting point is here and ending point is here. So to get that clear-cut information to the model and to understand it, we add this start token at the first of the sentence and end token at the end of this sentence, that is before full stop. Okay, that I guess we have mentioned here, auto-regressive manner. Yeah, shifting the output to the right ensures that the decoder generates the output sequence in an auto-regressive manner. This means that the decoder generates one token at a time using the previously generated one. And here I have even written, you can see here, by adding the start token at the beginning, we provide the decoder with a clear starting point for generating the output sequence. Okay, I hope you got this. That's the reason we add the start and end token. Output embeddings. The target sequence is converted into dense vector representation using the output embedding matrix. The matrix is learned during the training and mapping of each tokens to a vector in a continuous space. So here is how it works. So you can see here start might be represented as this particular embeddings. and the might be this particular embeddings cat and so on for other tokens. These are the embeddings which we create, embeddings matrix. So here you have an example embeddings matrix, and instead of seeing it here, you can see here. Now the output embedding matrix here you can see here E start. This E is representing nothing but embeddings. E start, E the till the end. So you have all the embedding matrix representations as well. To understand it more visually, you can see here E start, E the, E cat, E sat, sorry, EMB. Yeah, EMB. EMB is nothing but embeddings, and M end. So this is a visual representation which we have clearly created so that you guys can understand it very clearly. It took more time to create this. By seeing this effort, I expect at least you guys do subscribe the channel and encourage us to create more videos. And if you have any interested topic you want to learn, please make sure to comment below. I'll definitely create a video on those particular topics, whether it can be any large topic as well. I'll learn it and we'll create it as a playlist. So let's learn together. So this is our step 2 actually. We have added the embeddings. Okay, now, so start token and end token was your first step. Then we created an embedding matrix. Then we have that embedding data here. So that is our step 2. And step 3 is positional encoding. What is positional encoding? Since the transformer model does not have an inherent notation of the order of token, we add positional encoding to the output embeddings. This encoding provides information about the position of each token in the sentence or in a sequence. How it works. Positional encodings are added element wise to the output embeddings. For example, so this you have an example here. Before that, let me just give you in a simple terms why positional encoding is. So whether it be encoder or decoder, the transformer architecture had a positional encoder in it. Why? Because these particular models which have this processing ability or this embeddings whatever are coming in, so they don't have the ability to understand what position which particular model should be there. So to understand that, we created a separate entity, you can say, called position encoding, which will make sure that all the data or all the input sentences which are coming in should be properly aligned in the same position where it should be there. So in simple terms, how positional encoding? So the positional encoding's first token will be start. So here also the start and end will help the positional encoding to understand better. So when the start comes, okay, this is the first sentence. Okay. Then the next sentence, then next sentence. When end comes, okay, this is the final encoding sentence of this particular encoding word of this particular entire sentence. Okay. So that clarity, that particular positional encoding model will have if it has start and end. Okay. After that, it will make sure that, okay, next we have another sentence coming in. It's a new sentence because here the end token is there. It means that this sentence is over at here. So it has that clear picture over there. Embed start. So embeddings are done, then positional encoding. Then you get here positional encoding start. The cat sat on mat end. Okay. This is our output now. So this is positional encoding. After processing with positional encoding, whatever output we get, that is this particular output. So you have the example here, encoding and positional encoding output examples. So now what output embeddings with positional encoding will come like this. Start, embedding start plus positional start. So then you get 0.1 plus 0.0. So on, and you finally get 0.1, 0.2, 0.3. This is nothing but adding both and multiplying. Sorry, multiplying and then adding all of them. By seeing this example, you automatically get it. Step 4, masked multi-head attention. How it works. So about this, we created previously a detailed video. You can go and have a look on it. Here you will understand about it. So first, we have the input layers. The output embeddings with positional encodings are fit to the masked multi-head attention layer. Then the attention scores are calculated of the QKV. So we use the QKV and dot product and we calculate it. A mask is applied to prevent the decoder from attending the future tokens. It means that the given token of a position I it can only attend the token from position 0 to I. Means we create again a mask to make sure that it doesn't attend any other tokens apart from this particular fixed tokens. So for that we create some positions like 0 to I, specifying from here to this particular I or any value. Okay. If we are processing the token of cat position 3, then the attention mask will ensure that it only attends the start the cat. So if we give cat as a I, so make sure that it will make sure that the attention score or attention calculation will only output as start the cat. That's all. Third position we have fixed. So the data will start from 0 and it end at the third position. It is similar to indexing, you can say, to understand better. Then softmax operation. After applying the mask, the scores are passed through a softmax function to obtain attention weights. So once we get the score, then we process it to softmax and we get the weighted sum. The weighted sum of those particular computed instances, and then of the following v vectors, resulting the context vector of each token. So this we have already discussed previously. First we calculate the QK data, we take the masked multi-head attention, we process it completely, and once we enter into softmax site, at that time the attention weights and the V value, QK we have processed, but V values which we are having, we forgot that, we add that here with this particular attention weights and V, and finally we get the output. Then residual connection and layer normalization is done. The output of the masked multi-idle attention layer is added back to its input, and it helps model retain information from earlier layers. After adding the residual connection, layer normalization is applied. This normalization the output across the features, which helps improving the convergence during training. So here how it works. So whatever we get the masked attention model data, right, that we again feed to layer. This is after softmax. Okay, we feed it to a layer normalization, and afterwards we get the normalized outputs. Then that is at the step 5 where we process again to multi-head attention. So which takes an input of mask multi-head attention and the encoder's output. Now these both are taken. So this component is very crucial, allowing the decoder to attend both the previously generated tokens and the contextual information provided by the encoder output. Okay. So here is how it works. Input to the masked multi-head attention layer. The masked multi-head attention layer takes two set of inputs, which is the output of the masked multi-head attention layer and the contextualized output which we got from encoder. That output will also be fed. Then we calculate the attention scores of the Q vector and the output of the masked multi-head attention and the key vector derived from it, and allowing the decoder to focus on relevant parts of the encoder output while considering the context from the previously generated tokens. So here you have about it as well. The attention weights are used to compute a weighted sum of the V vectors, which also derived from the encoder output. This result is a new set of context vector. It incorporates information from both the encoder output and the previously generated tokens. So here you can see the normalized data, whatever we have, we again send that to QKV, and the encoder outputs also we send it, encoder output QKV data also we send it here. Then again multi-head attention process is done. Then we get the final data here. Output of masked multi-head attention. Then again layer normalization. So after this again what we do residual connection and layer normalization, and we get again the normalized output. Then step 6, feed forward neural network, which is nothing but you can say your ANNs. The input to the feed-forward neural network is the output of multi-head attention layer, which contains context vectors that has been informed by both the encoder output and the previously generated tokens. Now each token vector is passed through two layers. One is the first linear layer, increasing the dimensionality of the vectors, the ReLU activation function introducing non-linearity, and the second linear layer reduces the dimensionality back to original. Okay, so that is a simple ANN. If you understand that, it's very great. If you want a separate video on ANN, you can comment below. I'll create a video separately on it. If the context vector of cat after multi-head attention is 0.5, 1.3 and 0.3, it might be transformed as follows. So the first one, you can see here increased dimensionality. Here example is very clearly defined. So if this is your present layers embeddings, then this once you pass this is to the first layer, it will increase the dimension to 1 and 0.7. And again the ReLU activation function will remain same here. It will check it. Once the activation function is done, it will again send to the second layer where this is normally again reduced back to 0.4, 0.6 and 0.2. This is a better example to understand, I can say. After the feed-forward neural network outputs what we get, we again perform layer normalization. This is the quality check, you can say. So after doing this, once we get the normalization, then we generate output probabilities. How it works? Linear transformation. The output from the normalization, you can say adds and norms are nothing but layer normalization step is passed through the linear layers that set the output of the size of the vocabulary. It means that the each output vector is transformed into a vector of possibly corresponding to each tokens in the vocabulary. So here whatever we get, right, that is again transformed. Linear transformation is done and we get the weighted matrix and bias matrix of it. So here you have the weighted matrix output, and its output will be whatever output we get into weight plus bias. Again we do that. Then the result of the new vector represents the score of the each token. So softmax function. After this again we have softmax function at step 8. So I know encoder was very easy for you all. Decoder is very difficult to understand. So it's not a problem. If you see this, if you understand this step by step, you will understand it easily. And you all know one shocking fact. Whatever is done here, so the softmax is again applied to the output of the linear transformation to convert the raw score or raw embeddings which we get into a possibly distribution of the output of the vocabulary. This is essential. In short, it is like to get the vocabulary, distribution of the vocabulary. This is essential to determine the likelihood of each token being the next token in the sequence. And you all know the shocking fact. All these steps which you are seeing, these all steps happen in a second. So if you provide an input token, immediately you get an output token out within seconds. So how much fast the processing should be at the back end. So if you take an example of ChatGPT itself, if you ask a question, immediately within seconds it will start to generate the answers out. It is also working, GPT is working, it's a GPT architecture which is working on decoder itself. So then understand how fast will be at the back end that it's responding so fast. These many steps are taken at the back end to get one quality output. How softmax works and its exploration and normalization is here. So the softmax formula and the probability token and its ZI. So once we do that, you get here, you can see softmax token, the linear transformation, we get the sum of all the exponentiate values, then we get hit here. So once we take the sum, then we dive to the next calculation. So which is simple that after taking the linear right, then we enter into the softmax and from there we get all the sum of all the exponential values and finally we get the predicted output. So based on that we get the final output. So if you ask an English sentence to French, so after performing all these checks, it gives you in a French language actually. So this is the process which takes at the back end. So that's the reason the model is trained on huge data to work on all this. To have an example for calculation as well, you can have a look on this calculation to understand better of this output probability. Okay. The decoder can choose the next token in only two ways. One is argmax, which is select the token with the highest probability to the straightforward method, and sampling, randomly picking the token based on the probability. This adds some variety of outputs. So which is nothing but if you see, when it comes to us, if we don't know any question, answer, if we don't know right about any question, we will tell, okay, I don't know about this. Even GPTs have that. If you ask any illegal information, it will tell that as a model I cannot answer it. But if you normally ask any question which the GPT model don't knows also, it will randomly pick out some information and it will try to make out some information. It will try to generate a wrong information. That is nothing but a kind of testing, you can say. It's all about trial and error. So it is just picking out the trial. So if the output is trial is successful, we accept the output. If the trial is error, then it will throw an error. Then it will again start with the next trial. So it's all about this. All the AI models are nothing but they are trial and error methods. So it's a kind of reinforcement learning models. So you have to teach it. Whatever you give input, it will understand it. Based on that, it will again retrain it. So only these models are that powerful. So these are the again examples and the iterations of it. So you can just have a look on it to understand more detailedly about decoder. I would recommend to check out this particular blog. Blog link will be in this video description. And make sure to follow me for more interesting content, and do subscribe the channel definitely, and like the video and share with your friends if you want more interesting content. Okay guys, so let's meet you all in our next video, that is video 9, where we are going to discuss about the final transformer architecture. Let me just show you all will get shocked after seeing that. So this is the final transformer architecture which has everything, whatever we discussed till now, all the 8 notebooks, concepts, whatever we have, right? Combination of that, you will get it here. This is the encoder and this is the decoder architecture. I'll explain you all in detail in next video, and we will do even code implementation as well. That will be more interesting. Stay tuned for the next video.